Morning lads, I've decided to carry on from the previous video and now do 24 numericals on the concepts of solubility product to reinforce the understanding of how this reaction kinetics concept links with the GCSE caliber concept of solubility. So solubility is the rate of dissolution of a particular salt in unit volume of its relevant solvent, mostly water, mostly salt dissolving in water, and at incremental temperature tiers. And as we discussed yesterday, it was all about dq over dt equals mc delta t. Whilst doing numericals, you'll have to make sure that the multiple is converted into an exponent. So for example, if it's 2Cl, so in the equation, it'll become the concentration of chloride squared, so that'll be squared. And then you have to learn to reverse the calculations as well, and when you do reverse them, you'll have to perform underrooting, root of fifth root, fourth root, third root, depending on whether they were pentupled, quadrupled, or trebled. Always resolve the ionic equation prior, and remember that salts, whether they be carbonate, phosphates, hydrogen carbonates, phosphonates, silicates, nitrates, hydroxides, oxides, they will vary in the solubilization. Solubilization is the process of incorporation of solvent into of solute into solvent per unit time, per temperature tier. And you have to remember the principles of crystallization, recrystallization, displacement, and double displacement. And one example of double displacement is thermite reaction where aluminium and iron oxides are competing for each other based on their position and their reactivity series. So we're going to start off, and the first question is what we did yesterday. It was pertaining to lead sulfate, and the second question will be about lead iodide. Third question will be barium sulfide. So I'll start off. So in question 1, the salt under observation is lead sulfate. Both are bivalent, so they are equimolar in ionic distribution. So the first ion would be lead 2, and then the second one would be lead sulfate. Sulfates do not decompose under electrolytic pressure. So that'll be if the concentration so the concentration of lead sulfate in the fluid was 1.26 times 10 to the power exponent minus 4 moles per dm cubed. And so by ratio proportionation, lead ions and sulfate ions would have the same concentration. Now when you perform the solubility product equation, it would be lead and sulfate, and when you multiply, it'll practically be a square, and so when you square it, it would become 1 point, I'm supposed to but if you square it, it would be 1.6 times 10 to the power exponent minus 8 molarity squared, which is moles squared per dm hextupled. Right, the second question is it pertains to lead iodide, And so lead iodide, it will be PbI2 because for obvious reasons, valency combination. Lead is 2 positive. It could be 4 positive as well, but mostly lead exists as 2 divalent. And then it'll be now if the concentration of lead is 1 nanomolarity, if it's 1 nanomolar, then lead would be nanomolar, which means 1 times 10 to the power minus 9 moles per dm cubed, and that'll be 2 nanomolar. Yes. Now when you're calculating the solubility product, K subscript SP, it'll be in this format, because as I said earlier, exponent multiple becomes exponent, and then that'll be singular, and this shall be doubled. Yikes. So that'll be 4 times, hang on, it's 2 exponent minus 9 answer squared, that'll be 4. Oh yeah, so for the answer would be 4 times 10 to the minus 27 molarity cubed, which would mean it's mole cubed per dm 9. Moving on to the next question, which is about bismuth sulfide, which we did yesterday. Bismuth sulfide, and it would be a highly disproportionate equimolar distribution. If the concentration of it's in water, because it's not very soluble as I predicted, so the value for its molarity in molar solution is 1 times 10 to the minus 97 moles per dm cubed. So this would be bismuth would be 2 times 10 to the power minus 97 plus and sulfide would be 3 times 10 to the power minus 97 moles per dm cubed and moles per dm cubed. Now when you're calculating the solubility product, the multiple would transform into exponent, which will I'm so sorry, it should be 3 positive, I apologize, 3 positive squared multiplied by sulfide double negative cubed. This is turning out to be a bit more taxing for the in terms of the arithmetic, so let me now this you'll have to multiply 2 exponent minus 97 squared times 3 exponent. I should not be writing it like this. Cubed. So the final answer would be, so first of all you cube it. Oh my god, that is too large a figure for the calculator, so bear with me please. Oh my goodness, hang on. Oh no, it's okay, so 4 exponent 194 and 3, so 27 exponent is 291. So then you multiply this large number and it'll be 27 times 4, 108, 108 exponent minus 485. That's a the solubility product is minuscule, puny. So that's how it is. And if we said, look, now I'll show you how to reverse calculate it. Let's assume that the solubility product of bismuth was 1 exponent minus 97 moles. If that was the actual solubility product of bismuth sulfide, what would be the eventual individual molarity of each? So we could see that so it should be 2x and 3x. And so it was more twice the concentration of bismuth sulfide. This was thrice the concentration, according to the equation here. The equation tells us this, and that'll be 5x squared. And I have to multiply it. That'll be 2 times 1098 x squared, and we underroot it, and that'll be so this is the value of x. We have to reverse check and verify it. We have to reverse check and verify whether this would fall true. So in order to check it, we would do KSP equals bismuth and sulfide. So we would take this and 1.41 times 49, and we would square it, and then we would take 1.41 times 10 to minus 49, and we would cube it. So now we'll check whether this happens, and we'll do 1.41 answer. Again, it's not responding. Okay, so this is how we'll have to reverse check it. So this, if you wanted, because this number was too large, and for ease of calculational analysis, look, some salts don't dissolve at all. They're very, very hard to dissolve, very tough. They are extremely insoluble in water, and with them we write INS or we write PPT as a state symbol, because they're very, very insoluble. Like platinum, for example, if there was a compound called platinum carbonate, very difficult to dissolve. Gold doesn't form any compounds. Aluminium would form aluminium oxide, which is very hard. It's extremely tough to break, and that's the anodized layer on aluminium. So that's why compounds like this that are crisscrossing and have a very, very high intensity, strong coulombic bonding, molecular, covalent or electrovalent, and extremely insoluble they are in polar or non-polar solvent. It takes a lot of hydration and enthalpy to solubilize them. Now moving on to the other, this was just a demonstration. Now this was the real answer. This one was the real answer that I personally manually did, and the calculator broke down because it can't go to minus 485. But this is what I did reverse. So I assume that if this was the actual solubility product, what would be the eventual value of X? Moving on to the next question. The other thing you need to realize is that whenever you come across grams per liter, you have to bring it to grams per dm cubed. Then you have to bring it to moles per dm cubed and write it as M, capital M. Don't write it as mole per dm cubed because examiners already know what you're doing, and they know the big M stands for molarity, which is moles per dm cubed. So grams per liter is molality, and they'll give you the value in grams per liter just to see whether you could do the arithmetic by using C1V1 equals C2V2, C1V1 over N1, C2V2 over N2, and the rest. The next question I have for you is, the solubility of calcium carbonate at room temperature pressure, which is 298 Kelvin, is 6.9 times 10 to the power minus 5 moles per dm cubed. Calculate the solubility product. So it's very straightforward. So we ionize calcium carbonate without adding water in there because don't have the space, and we don't need to either. So solid ionizing into CaCO 3 ionizing. It's both are bivalent, so it's the dissociation is ionic dissociation is equimolar. So if the solubility product, if the molarity is if it's 6.9 times 5 to the mole per dm cubed, then this would be the same. It would be the same here as well, and same here. Sorry, writing takes a while. And then when you do the calculation of solubility product, just square it and see what you get. 6.9 exponent minus 5. 6.9 exponent minus 5 squared. That's 4.76 times 10 to the power minus 9 molarity squared. I mean, they gave you the answer as 4.8, but I would never write 4.8. I would write 4.76 because this is FE caliber. And as FE in the exam, paper 5, paper 4, you have to give it as 3 sig fig or 2 dp. So 4.76 nanomolarity squared is the correct answer. But don't put an N instead of this one because you would confuse the examiner, because the examiner would assume it to be like this, whereas you're meaning it to be this. So either you put all the stupid brackets or you don't bring it into nano configuration, because although it's nano, 4.76 nanomolarity squared, but the examiner would assume it to be this, which would render your response incorrect. The second question is about calcium sulfate at room temperature 298, and it's given in grams per dm cubed. So you have to find the concentration now in moles per dm cubed. So we know that calcium sulfate, it's a bit of a molar exercise. So question number 4. So calcium sulfate would ionize as? Would ionize as? And if it's so the MR, so it's equiproportional, and the ionic dissociation and if it's so the MR of 72, and so 40, 30, 70, 130, 136. 16, 90, 130, 136. Now, if you calculate the number of moles, it'll be 0.67 grams per. So in 1 dm cubed, we're assuming that the solution is 1 dm cubed, so it'll be 0.67 grams divided by, so the number of moles would be 136 grams per mole. Gram cancels and mole comes on top. It'll be 4.9 millimoles. And so if is that correct? So hang on, sulfate is 32 plus 64 plus 40, that's 136.0.67 divided by, that's 4.93 millimoles. So if this is 4.9 millimoles dm cubed, calcium ions and sulfate ions would express the same concentration because of their bimolar equiproportional ionic dissociation. So this would be 4.93 times 10 to the power minus 3 millimoles per dm cubed, dissociating into millimoles per dm cubed. And then you can just square it to find the solubility product, which would be 2.43 times 10 to the power minus 5 molarity squared. Is that correct? Yeah, that is correct, yes. And the next question would be, so this is what we did. It's very straightforward. The only thing you had to do was find the number of moles, keep the volume constant, assume V equals 1 dm cubed. Yes, that's it. And the next question is lead chloride. So it'll be lead chloride. Chloride expresses double ionic concentration, then lead. and if a lead chloride concentration is 0.16 moles dm cubed, room temperature, pressure 298, it would be the same. And it will be the double. There we go. Now equation becomes singular versus cubed, so you'll have to, the solubility product would be whenever always in the exam, do not ignore this part. You have to carry on writing the value that's what you're calculating here. Most students I've come across, they forget to write this part down to bring it down. Very minuscule, but it's an aesthetic component of calculational analysis that you need to be mindful of. So 0.016 times 0.032 squared, that'll be, I hope my calculation is correct, 1.64, rounding it off to 3 sig fig and 2 dp, that'll be molarity cubed. And the answer is correct. That is correct. And so just look at the sequence one more time. Resolve the ionic equation. Lay out the molar ratio proportionation. And devise the equation, fill it out, numericalize it, and get the answer. The next question I have for you is calcium phosphate, the very important bone structure component. Calcium phosphate, very interesting because it's highly disproportionate like aluminium. Gotta be careful. Aluminium phosphate, and when it dissociates, it's highly imbalanced. It's not equimolar proportionation. So if we have, oh my goodness, so it says, it's asking you to convert 7.7 times 10 to the power minus 4 grams per dm cubed into moles per dm cubed. So we just have to calculate the MR, molecular mass of calcium phosphate, which would be 120 grams for calcium, 120 grams per mole for calcium, 3162 grams per mole for phosphate. 8 times 16 is 128 grams per mole for oxygen. That'll be 248, 250, 310. 310 is it? Yeah, 310 grams per mole. 310 grams per mole. So you, in order to get the moles, which is C over, so M over MR, I mean, not R, this isn't R, but it's molecular mass. So it'll be 7.7 times 10 to the power grams divided by 310 grams per mole. Gram cancels, mole comes on top, and that'll be 7.7 exponent minus 4 divided by 3110. That's 2.5 micromoles. I'm going to write 448, sorry, 2.48 micromoles. I shouldn't be writing this, but this is how it is, micromoles for physicists. Now we're assuming that if the volume is constant, it should be 2.48 micromoles per dm cubed. So I would write it like this. Because there's no square or cubing involved, the examiner wouldn't be confused this particular time. But when the molarity is being doubled, trebled, or quadrupled, or pentupled, as is the case with solubility product numericals, please do not add Greek symbols to minimize the exponential power of the molar solution. Okay, so now it says, so now we know that the actual factual the molarity of calcium, and I'm using a blank marker here so you can understand it, is this. So now we're going to equate it. As per this equation, so it'll be treble for calcium and twice double for phosphate. Oh my goodness, hang on. Yeah, so sorry, not, yeah, well, it's adding here, but we wouldn't add it. So the equation that would form is, you already know this, is calcium is going to be cubed. Calcium concentration shall be cubed further. So, I mean, it was trebled, and it's now going to be cubed. And phosphate was doubled, and it's now going to be squared. So trebling to cubing, and doubling to squaring, and that will be this will be our equation. We'll have to plug it in here and cube it, and plug this in here and double it. I wish I had more space in the same page. You're going to have to use a thinner marker. So if I put 7.45 and cube it, 4.97, and double it, we get we get 1.02 times 10 to the power minus 26 molarity pentupled, and that's the answer. So this is how you need to solve it in the exam, and if you're running out of space, do what I did and save yourself a lot of headache. Now halides, I'm going to shine a bit of light on halides. What are halides? I spoke of it yesterday. Halides, my goodness, it's running out. Bear with me, please. Halides are ionic compounds of group 7. Primarily chlorine, electronegative entity. Sorry, should be in fluorine, chlorine and bromine. Sorry about that, I apologize. Fluorine, hydrofluoric acid can melt glass, and bromine, bromides are popular. Now, these are halides. They should not be confused with nitrogen, oxygen, NOF, which is used in organic chemistry. The NOF thing that's used as a symbol of electronegativity is used in the chapter of periodicity, and periodicity and organic chemistry. So they should not be confused with that. NOF species are different. It's used in a different context. So we are here talking about chlorine, fluorine, bromine, fluorine, bromine, chlorine, in terms of halides, and halides are actively dissociative in water, so they readily dissociate, giving out ionic dissemination, ionic activation of the compound. So the most popular chlorides you'll come across is NaCl, Cacl2, Mugl2, magnesium chloride, calcium chloride, sodium chloride, lithium chloride, cesium chloride, francium chloride. You're not going to come across very often because cesium, francium are radioactive or highly charged, highly active. They're not used in calculational purposes or experimental analytical chemistry. They're not used in simpler analytical chemistry experiments. So sodium chloride, calcium chloride, magnesium chloride, that's alkaline earth and rare earth alkaline metals, group 1 and group 2. And yeah, you will come across lithium chloride a little bit, very rarely, but the most common ones will be these 4, and that's pretty much it. And then when it comes to fluorides, it'll be hydrogen fluoride, sodium fluoride used in toothpaste, calcium fluoride, magnesium fluoride. It's basically calcium, magnesium, sodium of every kind, and lithium fluoride. Yes, lithium fluoride is used. Then it'll be sodium bromide, magnesium bromide, MgBr whole twice, calcium bromide, and lithium bromide not so much, but yeah, I'll just mention it to satisfy the deed. This is what halides are, and they're readily soluble. They'll have a lot higher, larger solubility dissociation values than, let's say, sulfides or lower activity series metals. So if I gave you silver bromide and determined its ionic molar dissociation to be equiproportional, and I said that it was 8.8 times 10 to the power minus 7 mole per dm cubed, which was the same here. So what would the solubility product be? The answer should be as follows. This is how you'd solve it without wasting any further time. You resolve the equation, write down the concentrations and how they would appear to be based on the molar proportionation, and then you just square it, because in this particular case it's all unimolar, and it would be basically squaring it. You are and that would be the answer. And if you got a question in paper 5 stating that magnesium bromide is being dissolved and the molality is 0.27 grams per dm cubed, what would be the solubility product? The solubility product, you'll have to find out by what we did in the previous question, the one before halides, is that you have to find out the molecular mass of magnesium bromide, which would be Mg plus 2 Br equals 24 grams per mole. You have to write grams per mole every time. And bromine would be 82, I think. Is it 82? More math. 80. So that'll be 80. That'll be 161.84. And when you divide it, you get 1.47 millimoles per dm cubed. So you divide it. Oh my goodness, hang on. Yeah, so it's grams per dm cubed divided by grams per mole. Gram cancels, and the mole comes on top, and dm cubed stays at the bottom, and the answer is 1.47 times 10 to the power minus 3 moles per dm cubed. And the solubility product from here onwards is quite simple, straightforward. .47 millimolarity, single, and then multiply it by 2, and it becomes 2.94 millimolarity for bromine, and you square it, and you multiply the square of it to, and then you get 1.27. The answer would be 1.27 times 10 to the power minus 8 molarity cubed. So the original concentration of magnesium bromide came out to be 1.47 millimoles per dm cubed, millimolarity, minus 3 that is. Then you take, it would stay the same for magnesium, and then you double it for bromide and then square it, and that's what you get. And that's pretty much it. That's how. And the other extent of difficulty that can be induced in this branch of quantification is that they can give you this, and then they'll make you find each of these two out. So they'll give you this, and then they'll make you find this and this, and for that you'll have to do a bit of arithmetic, algebraic arithmetic, basic algebra. Now that's going to be very simple if it's an unimolar or an equimolar compound. It'll be very easy if it's an equimolar compound. Alright? For an equimolar compound, for example, if they say, AgCl, silver chloride, which is halide, aqueous, it's unimolar on either side. And if they say that the solubility product is 1.8 times 10 to the power minus 10 molarity squared, what is this and what is this? That's going to be quite easy, because you just need to underroot it and you'll get the answer, which would be, so, but you still have to do the work. You'll have to actually write in everything, otherwise you won't get the marks. And so you'll have to put x here to the power 1, and then you have to put x here again, and then you have to do x squared 1.8 times 10 to the power minus 10 molarity squared, and then you'll have to 1.8 times 10 to the power minus 10 molarity squared, same thing, writing it over and over again, and you'll have to underroot it then. And yeah, so 1.3 times 10 to the power minus 5 mole equals x, yes. That'll be your answer. So that's called reverse. So this is a form of reversing, a reversal. Reversal of analytical assay quantification. So this is how you can reverse. The other kind of example you'll come across is where it's not equimolar proportionation. And if I gave you the example of for example, the example of let's say a sulfide, for example, if I can put in a sulfide there, sodium sulfide. Oh, sorry. And here we can see that the solubility product, if for example the solubility product was 6.3 times 10 to the power, very, very low, it's minus 51 moles cubed. So this would be 2x. So if the solubility product, sorry, not the concentration, obviously, please don't confuse it. So if the solubility product, the actual eventual answer, then you'll have to, so this would be 2x, and you'll have to square it in the end, and this would be x. So that would become 2x cubed. And then in solubility product, you'll have to do 4x cubed. Yeah, 4x cubed. So you have to do 4x squared times x. That'll be 6.3 times 10 to the minus 51 molarity cubed divided by 4x cubed. So sorry, equals 4x cubed, and then divided by 4, you get 1.5 times 10 75 times 10 to the power minus 51, and then you cube root it. You would get 1.16 times 10 to the power minus 17 moles equals x. So the x value, this is not, so the x would be, so sulfide would be this, and then so sulfide would be 1.16 times 10 to the power minus 7 moles per dm cubed, and then sodium would be 2.33 times 10 to the power minus 17. Sorry, that's 17 here. 1.16 times 10 to the power minus 17, and then this will be 2.33 times 10 to the power minus 17 moles per dm cubed. So that you'll not only have to specify and find out and numericalize this, but you'll also have to write the answers for these two ionic dissociative components as well. You'll have to write it at the end. So value 1, value 2, value 3. And that's your complete answer. Loss of marks will take place if you don't mention these. The other kind of question you need to worry about is if it's a trivalent ion. So for example, if it's chromium hydroxide, or associate it because chromium has variable valency because of its transition metal origins. So if the solubility product is moles quadrupled, then this one would be x, and this would be x cubed, and this would be x quadrupled, and you just have to after that you just have to take the fourth root, so this will be 3x cubed, and that'll be 27x4. 27. The answer will be 27x4. Thank you for. I just checked it. So this will be, because you treble and you cube the treble and you square the double, and it would be this. So the answer would be divided. The answer would be 1 times 10 to the power minus 33 moles quadruple divided by 27 whole fourth root, and that would be, the answer would be 2.47 times 10 to the power minus 9 moles. So it'll be nanomolar, and so this would be the concentration of chromium, and treble it would be the concentration of hydroxide ions. So you'll have to mention it here. Chromium ionic concentration would be and hydroxide ionic concentration would be and that's how you'd solve the answers. And in some cases they might make it extra difficult by giving you the molarity in grams per dm cubed, and then ask you to convert it into molarity. So molality to molarity, and then you'll also have to do the calculational analysis as I did. So you'll have to convert grams into moles per dm cubed, and then do the arithmetic. To find out the ionic concentrations. So individual ionic concentrations. That's pretty much it. These are the kind of questions you'll come across when tackling solubility and solubility product at HNC, HND, BTEC and sixth form level. There aren't any other kinds of questions apart from playing with the puzzle back and forth. And that's pretty much it. I'm glad. Thank you very much for watching this video. But I'd like to talk about, before we go, I'd like to talk about the common ion effect as well. The common ion effect, it's something like if you have a saturated solution of sparingly soluble substance A, and you mix it with a solution of substance B, which contains an ion in common with A, you can assume that the concentration of the common ion is the same as its concentration in B. So, morning, it'll be, so for example, if it's calcium sulfate in water and dilute sulfuric acid, and then if it's dissolved, so if calcium sulfate is dissolved first in water and then it's dissolved in dilute sulfuric acid, how would you go about calculating the the concentrations? So calculate the solubility of calcium sulfate in moles per dm cubed in water and then in dilute sulfuric acid. This is where the common ion effect would come into play. So calcium sulfate dry dissociation would be like this. It's it's bivalent equimolar proportionation when dissociating, but when you add it to water, it's sparingly soluble. So it would be weak conjugate, and so there will be a weak conjugate, weakly acidic, weakly basic combination. But the alkaline nature would dominate because you've got two alkaline and one acidic, committed acidic molecule. So if the total solubility product of calcium sulfate in water is 2.4, then how, what would be the individual ionic concentration? It would be x squared, so you'll have to just do x and x, and you'll have to take a root because both are bivalent equimolar. So the individual concentration would be yes. And now when you mix it in so now when you mix calcium sulfate into 0.5 moles dm cubed H2SO4 sulfuric acid, it would just form complexes: CaSO4 complex, HSO4 complex, H2SO3 complex, and all sorts of, like you'll see these phasing in and out. So basically this concentration will remain the same. So if you wanted to find out if let's just say if we had the solubility product to be the same, let's assume that, what would be the so here the concentration of this would be X, and this would be X plus 0.5 moles per dm cubed, because H2SO4, if it's 0.5 moles per dm cubed, so it would dissociate as 2H positive and 1 SO4 2 negative, and so the concentration of sulfate ions shall equalize that of sulfuric acid, but H ionic concentration would be diprotic concentration would be double that of the molecule. So in this particular case, whatever concentration you had in here, you'd have 0.5 moles of it, a little bit more on top of what you had in this previous solution. So the equation would be, in this particular case, would be KSP equals calcium 2 positive and sulfate 2 negative, and both are singular in exponents because of their equimolar ratio. And so if the solubility product was 2.5 10 to the power minus 5 molarity squared, this would be X, and this would be X plus. Well, now when you multiply it, you'd get X squared plus 0.5 X, and it will form a quadratic equation. So X squared plus 0.5X, and then you'll have to use the quadratic formula, unless you assume it to be negligible, this one, unless you assume this to be negligible. And they do, but I won't. I'll have to just use a quadratic formula where A equals 1, B equals half, and C equals 2.4 times 10 to the power minus 5 without the units. So you could also use alpha beta equals minus B over A, or alpha plus beta equals C over A. You could use this method, which is slightly longer, or you could use X equals minus 4A 2AC. You could use this to plug in the values, and you'd get and then you'd get the answer. So I've always used this method. I've never deemed it negligible. This is the the pure maths method, and this is the normal algebraic quadratic method. So minus B, because I'll give you the proof as well. So basically, when you do alpha beta square equals minus B over A, and alpha plus beta equals C over A, what happens is that when you square alpha plus beta, it becomes alpha squared plus beta squared plus alpha beta, and then it becomes C squared over A squared plus minus B over A, and then you resolve it. It's and then it becomes squared minus AB. So that's one form of it. Hang on, we need to bring it into b squared plus minus 4a or 4ac over 2a. So that we'll have to do alpha in an equation where you have a squared plus b plus c equals 0. Alpha beta is c over a, and alpha plus beta is minus b over a. Now when you square alpha plus beta, you get alpha squared beta squared plus 2 alpha beta. When you do get that, you'll have to plug in the values here. So that'll be minus b over a minus b over a c 2c over a. And then when you begin to resolve it, you find out it comes out as the quadratic formula. So then it'll be b squared over a squared plus 2c over a. So this is the final form. And when you further resolve it, it becomes wow, the kitty cat is so this is what it becomes. So now I've produced a neater form for you, and then this neat form would really help you understand the quadratic formula that we're about to use. So it's a rather neater version, and it allows you to see the discriminant outcome. So alpha beta squared, and then it brings the raw form of quadratic equation out, and this one is where you can bring it in the form of minus b under root b and minus 2ac over and 4ac over 2a. So this is the basic discriminant. So that's that. LCM. And there we go. So this is what you'll use when dealing with disproportionate, unbalanced molar dissociation of compounds that have an not unequal combination of ionic components in their lattice. And if you don't ignore 0.5 mole per S, then you'll have to do all of it. You'll have to plug it into the quadratic equation, and You have to plug it in there. But if you want to make your life easier, then just ignore the S, and yeah, you won't have to use a quadratic formula anymore. The other question I'd like to tackle in a minute is about ammonia. It's a very large but a worthy question, and I'd like to go over it. This particular question asks, calculate the solubility of lead sulfate in 0.1 sodium sulfate solution. So it's another question about common ion effect. And so we've got two in the system. We have two components: sodium sulfate and lead sulfate. So we'll have double the concentration of sodium ions than lead ions under Avogadro's principle. So sodium is 0.1 moles per dm cubed. Sodium sulfate, and then the solubility product of lead sulfate is 1.6 times 10 to the power minus 8 molarity squared. And so we need to resolve it first. It's always in dynamic equilibrium, so that'll be and so this would be 0.1 mole, this would be 0.2 mole, and this would be 0.1 mole again. So this is how we know, and the solubility product would be 2x squared and x. So the solubility product for sodium sulfate would be 4 molarity cubed. That's the solubility product of this, and the solubility product of lead sulfate is 1.6 to the power minus 8 molarity squared. So now you can see that just by numerical analysis and comparison, you can see that the solubility of lead sulfate is far lower, at least 250,000 times lower than that of sodium sulfate, for obvious reasons, because lead is at the lower tier of activity series, and lead is a very inert compound and doesn't form sulfates and compounds under normal room temperature. It needs to have hot acids and hot alkalis to react with. What it's asking you is to find the concentration of lead, and we can see that in a solution of lead sulfate and sodium sulfate, this sulfate would be 0.1 S plus 0.1, and this would be S only. So the equation for lead sulfate would be S and S 0.1, and the solubility product would then be 1.6 times 10 to the power minus 8 molarity squared divided by S squared plus 0.1 S, and there we go. So A is equal to, B is equal to, C is equal to 1, 0.1, and minus 1.6 times 10 to the power minus 8 moles squared. And you can plug it in the in this equation, which is quite a lot of calculator jargon. So yeah, 0.1 squared minus 4 times A times C divided by 2A, that gives you the S or X, and then you can find S from there, and the X would be, S would be equals to X. Common ion effect was the epitome of it. The question we're moving to at the moment is going to be about ammonia, and with ammonia, before you tackle the question, you need to realize that ammonia may have this formula, but when it's mixed with water, it assumes ionic form, covalent form, and ammonium hydroxide becomes a very, very strong alkali, and it has a very high solubility, around about 1300 grams of ammonia, centimeter cubed of ammonia, and 1 cm cubed of water, which is why it's very pungent. So it's an alkali. Now the question says ammonia is a weak base which reacts with water to produce hydroxide ions. A 1 mole dm cubed solution of it would have hydroxide ions in the concentration of 4.2 millimoles dm cubed. That doesn't make any sense, but if you dissociate ammonia again ionically, it would be NH for ammonium ions and OH ions. And so if it's 1 mole here, it should be 1 mole here, but it's not. So if this was, if 1 mole per dm cubed, which is 1 mole would be 14 grams of nitrogen, 5 grams of hydrogen plus 16 grams of oxygen, that would be 35. It would be 35. grams per mole. So what you're saying is if it's 1 moles dm cubed, it's 35 grams dissolved in of ammonium hydroxide dissolved in 1 dm cubed of water, but in actuality it's 17 grams of ammonia dissolved in 1 liter. So it's 17 grams of ammonia in 1 liter of water, which is 1000 cm cubed, which is 1000 grams, and around about 55.6 moles of water. But overall, a 1 mole dm cubed solution of ammonia would have a concentration of hydroxide ions to be 4.2 millimoles per dm cubed. We have to take it as it is. It's not intuitive here, but I don't agree with it, but that's how the question says. So 1 mole per dm cubed of NH4OH has 4.2 millimole per dm cubed of hydroxide ions. Yes, that's the highlight statement. And then ammonium hydroxide is made to react with calcium nitrate, strontium nitrate, and barium nitrate, and all of them are bivalent nitrates. And it's saying if the same nitrates were then reacted with sodium hydroxide, which would have a higher tendency to form a precipitate. Would a solution of sodium hydroxide form more precipitates with calcium nitrate, strontium nitrate, and magnesium nitrate, or would ammonia form more precipitates with magnesium nitrate, calcium nitrate, and strontium nitrate, group 2 nitrates? So this question is particularly basically asking you to compare the solubility products, and lower solubility products would mean that it's a higher chance of precipitate formation, whereas a lower so if the solubility products are comparatively are higher, are of a higher value, then it would mean that it's more dissociated if it's solubilized effectively, and it's very, very soluble. So higher the solubility product, higher the solubilization degree, and lower the chance of precipitate formation. And so in this particular case, ammonia is a weak base that reacts with water to produce ammonium hydroxide, and in 1 mole dm cubed solution of ammonia, the hydroxide concentration would be 4.2 millimoles per dm cubed. 10 centimeter cubed of this ammonia solution was added in turn to 10 cm cubed of 0.1 moles per dm cubed solutions of group 2 nitrates. The experiments were then repeated with 10 cm cubed samples of 1 moles per dm cubed solution of sodium hydroxide. And it's asking you which base would yield most amount of precipitates. This is a simple question about comparing the solubility products. So higher the solubility product, like, you know, if it's closer to zero, you know, if it's lesser negative exponents would indicate a higher solubility product, hence a higher degree of solubilization, hence lower precipitate formation incidence rate. And if it's very, very negative, like it's very minuscule, lower the solubility product value, it would indicate a higher incidence rate of precipitation. That's pretty much what it's asking. That's all it is. But theoretically speaking, we have to first find out the hydroxide. We have to find the solubility product first, and then we can take it from there. So we'll have to find the solubility product of ammonia first, and then we'll have to find the solubility product of sodium hydroxide, and then we can obviously guesstimate which one would yield more precipitates. So first of all, we'll be doing we'll do sodium hydroxide. Now in sodium hydroxide, we've been told the concentration, the volume, and the number of moles. We'll have to find out. Bear with me, please. So in sodium hydroxide, volume is 10 cm cubed. Concentration is 1 moles per dm cubed, and so we'll have to see how many moles are being used. So that'll be number of moles is concentration. So C1, we know C1 V1 equals C1 V1, and then it'll be so N equals C over V. No, hang on. So N equals CV, and then it would be 1 times 1 moles per dm cubed times 10 over 1000. It'll be number of moles would be 0.01 mole. So if it's 0.01 mole for sodium hydroxide, it would be the same for sodium and same for hydroxide here. And you can see that the concentration of hydroxide ions in sodium are .34 times higher. So sodium hydroxide is 2.34 times stronger than ammonium hydroxide. So so when you so now we'll have to do a solubility, find out the solubility product. So the solubility product shall be sodium hydroxide. In 10 centimeters cubed of solution, it would be 1.10 to the power minus 4 moles squared. Whereas for ammonia, it would be it's far weaker. So solubility product of ammonia is far less than solubility product of sodium hydroxide, and so its incidence of precipitation would be far higher than sodium hydroxide. Sodium hydroxide would effectively dissolve all these group 2 nitrates far more effectively. So that's the conclusion based on qualitative stoichiometric analysis. Now, bear in mind, the answer is correct, but both will form precipitates nonetheless. However, the incidence of precipitation in ammonia will be far higher because by its very chemical nature, so when ammonium hydroxide reacts with a strontium nitrate, and then it would react with magnesium nitrate, calcium nitrate. In all these cases, it would form ammonium nitrate, and magnesium hydroxide, strontium hydroxide, and calcium hydroxide as part of displacement and double displacement dynamics, reaction kinetics. And we know that ammonium nitrate is, so it would form an orangish sort of very orangish precipitate. The precipitation would take place, and then you'd have magnesium hydroxide, calcium hydroxide, and strontium hydroxide in there as well, which is milky sort of precipitate. So precipitation would take place in either case. If it but the as I said earlier, because of ammonium nitrate contaminating the hydroxide solution, and ammonium nitrate is an orange, sort of an orange precipitate, the incidence and the degree of precipitation in reactions involving ammonium hydroxide with group 2 nitrates would be far higher than sodium hydroxide, because sodium hydroxide is colorless in water, and you'll only sodium nitrate doesn't have a color, and so but you will see the color white precipitation of group 2 nitrates, group 2 hydroxides. So when you react NaOH plus all of these, you'll get nitrate. You'll get nano 3, and then you'll get the OH complex with the X2 positive. So X2 positive bivalence, calcium hydroxide, strontium hydroxide, magnesium hydroxide, and then nano 3 doesn't have a color. It's like a colorless liquid. It's highly soluble, so it has a very high solubilization. But ammonium nitrate doesn't have a high solubility. It forms an orange precipitate. So as we predicted, according to the qualitative stoichiometric analysis, because of the solubility products values of ammonium nitrate being more negative than sodium hydroxide, we can already predict that although precipitation would take place in both cases, but it would be far higher for ammonium nitrate because of its low solubilization, and would be far higher for sodium hydroxide because it's far more soluble, and its compounds of byproducts in sodium nitrate is far more soluble. This was a very strenuous sort of a question, but people who have a strong grip on analytical chemistry and know about the theoretical solubilization variance in nitrates, phosphates, carbonates, bicarbonates, sulfates, nitrates, they would be able to predict the answer. So yeah, I mean, you can check. So sodium nitrate is a very colorless sort of a solution. So I'd like to recap our progress. We all started from the basic idea of dissolving solute ionic salts in warming water, and then observing the limit of saturation, supersaturation, drawing a graph, plotting the graph, performing basic unitary graphical analysis in form of interpolation, extrapolation, then mingling stoichiometric, volumetric analysis with it to give it a bit of substance, and then taking it from there all the way to solubility product, which is a hardcore part of reaction kinetics. And then and then progressing in level of difficulty, in degree of difficulty per question, and then also doing a reverse arithmetic analysis of every question as well, and seeing how quadratic equation relates to this reaction kinetics, because we use differentiation, integration in rate equation proofs, first order, second order, pseudo order rate equations, and so here we use quadratic equation for numerical simplification. It's been a very long video, but I hope you'll be able to take the message home and understand that this topic deserved the attention, because it combines, it's quite synoptic in its basis, and it combines the concepts of thermodynamics, reaction kinetics, basic analytical chemistry, and of course arithmetic, quadratics, and you end up exercising quite a lot more than what you bargained for. So I'm glad you stayed with me all along, and I hope you make the most of it. Wish you all the best, and I'll take it from here. Thank you very much.